It should come as no surprise that after finding the electric potential from point charges, we need to extend that idea to other geometries. Well, we won't deviate very far from a point charge. We'll just go to a conducting sphere. So here it is. You know the charges distribute themselves on the external perimeter. I should say the external surface. The total charge on that surface is Q. We have radius of the sphere is big R. We're going to put a Gaussian surface, even though officially it's not a Gaussian surface. It's just some radius R. And at radius R, we're going to consider what is the potential. So for R, little r greater than big R. Well, this looks like a point source, as you would probably guess. So V is KQ over R. Nothing different from that than just a regular point source. Now at little r equal to big R, namely at the surface, we have just the same idea. It's just KQ over big R. So that's the potential at the surface and beyond. Now what about underneath the surface? So inside the conductor, this is a conducting sphere. You already know that the E field is 0. So obviously the potential should be 0 too, shouldn't it? I mean, let's see, we integrate the E field, integrating 0. Don't we get 0? Seems like. Well, consider that no work is required to move the charge anywhere inside the sphere. There's 0 work to move it around. Therefore, the work in moving it from one location to another location inside here is 0. Well, that's the you divide 0 by the charge and you have, well, 0, but that just means that the change in potential across a region inside the conductor is 0. So no potential difference inside the conductor. That's not saying that the potential is 0. We already have that the potential on the outer surface is KQ over R. If there's no potential inside, then what does that mean? That means that the potential is KQ over R. It's what it was on the surface. There's no change inside. So this is really an important thing, and it's extremely easy to forget, to distinguish between the electric field being 0 and the potential being constant, namely what it is on the surface. And that's, in fact, what the situation is. So it's not that it's 0, but it's constant. It's whatever it was or is on the surface. Now we are ready to graph the electric field and voltage. So let's go ahead and graph the electric field. That's easy. 0 from 0 to R, and then it follows an inverse square law after that. So KQ over R squared is the initial value outside the sphere, and then inverse square. Potential, we have a constant value, not 0. It's what it was or is at the surface, which is KQ over R, not R squared. And then after that, how does it trail off? Well, here's the potential, and it's inverse R, not inverse R squared. So inverse function, that's just less curvy. And there's our first example of plotting the electric field and potential in all of space from this charge distribution. Well, now let's consider a very interesting effect known as the corona effect, or corona glow, or corona discharge. Starting with a conducting sphere, at the surface of the sphere, the electric field, KQ over R squared. The voltage, KQ over R at the surface, which happens to be E times R, which can be thought of as that electric field that exists here at the surface. If it was, I know it's not, but like if it was constant through this space, then you integrate that and you would end up with the E field times R to give you the potential. But really, the potential here is based on integrating the E field out to infinity, and that would give you the same result as well. So there's really no E field inside here, but the E field that exists out here is this value, and the potential is this value, which mathematically equates to E times the radius of the sphere itself. Okay, so if the electric field at the surface is greater than 3 million volts per meter. Now 3 million volts per meter is a pretty significant E field. You don't have much to use as a basis for that, but it's a large E field. When that happens, then you could say forces on the subatomic particles, namely the electrons, are such that it starts ripping them out of their atoms. You reach that energy threshold where the air will ionize. And when it does that, it becomes conductive. And that's about 76,000 volts per inch. That's what that corresponds to, 3 million volts per meter. In fact, that's what a lightning bolt is. The air becomes conductive, the charges are separated in the atoms, and the electrons flow from one to the other, or just completely are removed. They're ionized. Now the maximum potential then that can be achieved at the surface of this sphere, which is going to be the same all through it. If it's solid, if it's hollow, it's just all along the surface, is the maximum E field times the radius. Well, the maximum E field is 3 million volts per meter. So that's how many volts you can have, the potential at the surface of the sphere. Now with that in mind, let's consider a car antenna. You might have seen a car antenna. You might have something that looks like this on your car or your parents' car. So we have a little ball that sits on top of a wire coming up. Let's say for sake of argument that the radius of that little sphere is 2 millimeters. Then the maximum potential associated with that ball at the surface of the ball would be the maximum E field times the radius, 0.002, which is 6,000 volts. So there's a reason why that ball is on there. Let's consider the case where the ball isn't there. So no ball. No ball, let's say that the radius now is 1/10 what it was before, 0.2 millimeters. Then the maximum voltage that can be achieved without causing a discharge or without ionizing the air is the maximum E field times 0.0002, and that's 600 volts. Now, to give perspective on this, it's not like the electric field just exists across that tiny, tiny region, and that times that E field times that tiny space is where the voltage is built up. Even though we can think of it that way, because that translates into how much voltage you can have mathematically across this tiny radius. This E field times this tiny radius is going to be 600 volts maximum before ionization occurs. But the voltage itself is built up along the wire. So we got this length, and so we have 600 volts is really E times L. The electric field that exists in space from whatever sources times the length of this wire will produce really a charge separation, which then results in a voltage, a potential at the surface of that little radius. Hope it probably is confusing. But in any case, this E times L, being only 600 for the voltage that's really built up along here, is a very wee little small electric field times the length. So because this number is small, this E field is small. In other words, you don't have to have a very large E field before you really exceed the E field at the end of this wire, where that large E field is manifested, namely the 3 million volts per meter. All right. So in a practical sense then, we put the sphere, that metal ball up there, to reduce the possibility of a corona discharge. So it's a relatively small potential, 600 volts, and that's the point that will result in the ionization of the air, or the corona discharge, the corona glow. And static occurs, especially if you have an AM radio. You will hear static at that point, even with a small external E field. It's like a little mini lightning bolt. So hopefully that gives you some substantiation for why you would want a little metal sphere on top of your antenna. Now, Van de Graaff generator. How do we get such large sparks? Well, we have a very large sphere here. In fact, 15 centimeter radius. Now we can pump charge into this sphere, increasing the electric field because it's proportional to the charge until Vmax is 3 million volts per meter times 0.15 meters. That gives us 450,000 volts. So we can have 450,000 volts of potential at the surface of the sphere. Now, considering that 76,000 volts per inch is the size of E field that will cause ionization of the atmosphere, that should result in ionization through a region of space about 6 inches. So we can produce 6-inch sparks with a Van de Graaff generator of this size. So make sure I demonstrate that for you.